Hi guys, welcome to Module 3. This week we're going to talk about server-side technologies and security and contrast that with some of the client-side technologies that we talked about last week, which hopefully you enjoyed. At the end of last week and last week's assignment, we transitioned a little bit away from the client-side technologies over to the server side. We talked a lot about REST endpoints and how we can use them as an API, and how we can use different HTTP verbs to interact with functions inside of a web framework. So in the assignment last week, we looked at something called Flask, which is a micro web framework that's written in Python. And as you know, there are many different web servers that exist. Probably most of us have heard of Apache, which is an open source web server, one of the most widely deployed in the world. You might be familiar with Microsoft's equivalent, which is called IIS, which is Internet Information Services. But there are many more that you might not be aware of. You see here there's Light HTTPD, which is pronounced Lighty, which is a very, very lightweight, flexible, extensible web server. A little bit different than Apache. The footprint is much, much smaller. Jetty, you see here, which is a web server that is really great at running Java servlets, and there's tons more. So different web servers are obviously good at different things, but in general, the base functionality that they all have is that there's some driver inside of each of those web servers that is designed to respond to the specified set of HTTP verbs. We talked a bit about those verbs last week. You should be familiar at this point with get, put, post, delete, head. There are a number of others, but these are the main ones. And the main difference that we run into when we talk about server-side technologies rather than client-side is, remember, your client is a laptop that connects into an actual physical server somewhere, whether it's in a cloud or a data center or something like that. But all of the heavy lifting in the server-side technology is done on the server rather than on the client. And as we'll come to see in the next slide, there's many drawbacks and there's many advantages to this approach. So we'll dig a little bit more deeply into that. So let's get started. Next, we'll take a look at some of the benefits of server-side programming, just like we saw some of the benefits of the client-side technologies from last week's module. Some of the benefits you can see listed here. The first, and maybe the one that contrasts most with client-side technology, is performance. When you think of a server, you're probably thinking of a large 2U, 4U, or maybe even an 8U server that's in a rack somewhere in a data center. And in general, you're right. The performance provided by these servers is much, much, much greater than that of the clients. You can think of servers probably have nowadays at a minimum 64 gigs of RAM, but usually it's much, much more. Many servers now ship with half a terabyte, so 512 gigabytes, or even a full terabyte of RAM just out of the box. And they often have processors that are capable of much greater workloads than those of our laptops. So they may have multiple cores or many multiple processors on board. So the performance that you get when executing a workload is much greater on a server than it is on the client. Another one that's probably obvious and something we're going to touch on in more detail in these lecture slides as well as this week's assignment is security. We talked a pretty good deal last week about cross-site scripting attacks, and you can see how they can fairly easily, if the user or the framework is not careful about how it protects the data, whether it's encoding it so that it's not executable in the browser, or a user being careful not to click a link that contains malicious JavaScript in it. The security concerns are a little bit different. They shift when we talk about a server-side paradigm. In this case, the data usually stays on the server and is processed until it's time to return an answer to the user. So this is really nice because data is not flying around in the wild. It's self-contained. It can be encrypted on the server, and it's less likely that a party can gain access to it from the outside. We'll talk a little bit more about server-side security mechanisms, specifically with SQL Server later on in the lecture, but just know that security is another benefit of server-side programming, but maybe more so a trade-off when you're gauging it against client-side programming. Another nice thing about server-side programming are that a CMS, which is a content management system, says here that it makes it easier to build a fully functional website. You might have heard of some of these frameworks. There are many of them now, but two of the main ones that come to mind are a framework called Joomla and another framework called WordPress. And WordPress is a PHP content management system, or CMS. And you can install these applications onto your web server right out of the box. And with just a few clicks and tweaks, you're able to get a fully functioning website with things like blogs, with custom user logins, things like that. You can tie it into a database on the back end very, very easily. So it's much more difficult to do that on the client side. In fact, it doesn't really make sense to have a CMS on the client side. So these CMSs that come fully prepackaged are another major benefit of server-side programming. But that's not to say that there aren't drawbacks to server-side programming as well. So last week when we talked about client-side concepts, you probably remember that I listed performance as both a benefit and a drawback. And that's actually not so much different when we're talking about server-side stuff. So you can see here that although a server is capable of performing a much greater workload in a significantly less amount of time, that can also be a drawback, because think of a popular website like a Google that's doing searching, or a social media site or something like that. These websites have millions and probably billions of views a day. And so though they're capable of withstanding larger workloads, they're also going to get a really, really significantly increased amount of traffic visiting these websites. So for that reason, you can think when millions of people are visiting a website, no matter how strong the server is, right, you're still going to notice a performance hit if that many people connect to it. So in order to combat this, these large providers stand up large server farms, basically, and they usually put some kind of load balancing mechanism in front to kind of evenly distribute the load across the back-end servers using some sort of heuristic. It could be response time, it could be number of clients connected. There are a few different metrics for doing this, but you definitely have to distribute that load very carefully. Otherwise, all the users will be affected by the performance degradation when too many people are connected. Maybe the best thing that a client-side technology offers is those nice dynamic updates that happen in real time in your browser. And they happen quickly, and it makes a great user experience, but that changes a little bit when we're talking about server-side programming as well. So the issue here is that it's possible for something on the server to change, but there's no way for the client to know about it or to load those changes automatically. So what has to happen is one of two things. First is the client can just simply reload the page, and it can say, hey server, give me the most updated version of the page that you have. And so if the server's made a change to that page since the last time the client loaded it, when they reload the page and render in the browser, they'll see those changes. So that's one. The client can poll the server for changes. Or alternatively, now there's some nice technologies exist where the work can be done on the server, and the server can actually push a change to a client. So using some sort of message queue, specifically there's a thing called an SSE, which is a server send event. And a client can subscribe to a message queue that's on the server, and every time a message gets published to that message queue, the client is notified, and that message also contains not only a notification of a change, but it also contains the change itself. So the server can push that change to the client, and then when the client checks the queue and realizes that there's a message there, the client will pop that message off, take a look at the change, and then can load it locally. So it's either a push or a pull, but a very different paradigm than strictly client-side programming like we saw with JavaScript. And then perhaps maybe one of the larger drawbacks are the security involved with server-side technologies. A web server in and of itself is nice to serve up static content, as we saw last week. But static content is really not of too much interest for us, right? We like dynamically updating applications. And so in order to accomplish that, we need a couple things. So first is an application server. And last week we looked at Flask, which is written in Python as an application server. but you're probably familiar with things like PHP. So that's a large, obviously popular web application. And then in addition to the dynamic updates, oftentimes we want to store data publicly. So on Facebook, obviously we store lots of pictures, we store lots of status updates and things that we like. Same thing with Twitter, and pick your favorite website. There's lots of either settings or preferences or content that we want saved about us. So we need a database for that as well. So now not only do we have a web server, but we have an application server running, and we have a database server running. And so even though those three things could potentially all run on the same physical server, they really enlarge the security footprint of the server-side infrastructure. So now we're tasked with not only securing the web server, but also the app server and the database as well. And we're going to take a look in the upcoming slides at how we can begin to achieve this level of security, but also why it can be problematic. So we'll start our server-side discussion by jumping in and talking a little bit about database servers. I'm not sure if everybody's familiar with them or not, but there's a number of different popular database servers that exist. Similar to web servers, there's a huge grouping, and some of the most popular ones I've listed here, but trust me when I say there are many more. The ones I've referenced here are just relational databases, but there are many new ones out like Redis and Cassandra that reference this NoSQL model, which is a non-object related, basically a key pair based database. But these are the most popular relational databases. So MS SQL is Microsoft SQL Server. MySQL is a popular free open source SQL Server. And then there's something called PG-SQL, which is Postgres or PostgreSQL. And there are drawbacks and advantages to each of them. So Microsoft SQL Server, for example, is extremely expensive, but it offers some nice functionality that some of the open source alternatives do not. Okay, but so we're going to focus on these three relational databases. And a database is simply a server that receives some sort of query in a specified query language, which we'll talk about. And the driver reads in that query specified, interprets it, might even do some optimization of the query, and then it's going to take that query and then throw it against some data and then return the desired data set. So specifically in these three databases that I have listed here, they use a language called SQL or SQL. So SQL stands for a structured query language and is a cleanly devised language that allows you to express different queries against the data with certain restrictions. It allows you to read data, which is a select statement that I have written here. It allows you to update data, to delete data, all sorts of different operations, but similar to the CRUD example that we saw last week, you can create, you can read, you can update, and you can delete. So the first SQL statement you see here is called a select statement. And the syntax for a select is very simple. So a database table, remember, is a tabular format. So every column in a database table represents a field. So maybe ID, first name, last name, email address, password, things like that. So the columns are the fields. And each row in that table represents an entry. So each row is an actual row of data. So when we say select star from a table, where tables just can be replaced by the table name in the database, select star means give me all records from the specified table. So it's going to give you each and every row, and it's going to give you each and every column for each of those rows. So that just tells you tells your database to please return each and every piece of data from the table. That's often not very useful, and in fact, if you have a really large database, that's going to be extremely inefficient to pull back a ton of data that you might not need. So another construct in the SQL language is something called a where clause. And you can use the where clause to put some sort of restriction on the data that's returned. So I'll give you an example here at the bottom. If we select star from a table called emp, which is short for employee, where income, so one of the columns are named keeps track of each employee's income, is greater than 100,000. So what this is going to do is going to select back all data. So it's going to return all columns to you from the employee table, but only where the income field is greater than 100,000. However, I mentioned earlier that having a database server definitely increases the attack surface and so makes your applications potentially more vulnerable. Remember last week we went pretty in depth into what a cross-site scripting attack was, and it falls under the classification of an injection attack because an attacker is able to, in the stored or in the persistent cross-site scripting example, we saw that an attacker is able to inject or embed malicious JavaScript code into something like a message board or forum so that when you unsuspectingly visit that website, your browser automatically downloads the content from the forum and inadvertently downloads a script which gets interpreted and run in your browser, which might lead to your browser being exploited. Unfortunately, SQL is not much different. So because SQL is run on the server side and it takes user input, then that means just like JavaScript, it's actually also susceptible to attacks that are that come from that injection class of attacks. So what this means is if we have a database, and it's pretty easy to tell when there's a database behind our application, we can start to probe and poke at that database and send it certain inputs and look at the corresponding output to be able to tell if it's susceptible to an injection attack. So I've written a small example here for you it's just a little blurb of PHP. And you can see here that input val is actually taken from the post method of a simple HTML form. So in this case, it's taking the value from the form and storing it in the variable input val. So next you see that we're going to go ahead and we're going to do another select statement here. So we're selecting the ID and the name field from a database table called students. And again, here's a where clause, but we only want that information from the students table where the ID equals input val. Now remember, input val was read in directly from the user from an HTML form. And remember also from last week that it's really completely unsafe to trust that in all cases, the input your user is giving you is safe or valid. It might be safe but not valid. It might be invalid but not safe, and all permutations thereof. And you can see in the third line here, when we say result is equal to PG query, and we send it a connection and a query. So what that means is we're querying against a PostgreSQL database here. We're sending it a connection string, which I haven't shown here, but that's just the username and password and port number and database name. So that's the information we use to connect to the database server. And we're also sending it our variable query here, which again, query is a perfectly fine, it's a valid query, but it is based on some user input that we might not necessarily be able to trust. So for example, someone may have typed in the number 3. And what this is going to do is going to give you the ID and the name from the students field for the student whose ID was equal to 3. And that's perfectly fine. But the question is this script really safe? What if someone didn't just type in the number 3? Is there something malicious that they could type in that would allow them to see more data than they would ordinarily be entitled to? And not to scare you or anything, but the answer to that question is actually yes. So it is possible for a user to inject, rather than malicious JavaScript like we saw last week, they can actually inject malicious SQL code into the query and then get your database, trick your database into returning all of the records, or maybe even worse. So we'll see here below. In the first line at the bottom, I've said that input value is equal to 1 or 1 equals 1. So what I'm essentially, if I had passed this into input val, the query above would say select ID and name from students where the ID is equal to 1 or 1 equals 1. So think of your Boolean logic, and or is true So if we say A or B, that clause will evaluate to true if A is true, or if only B is true, or both A and B are true. Okay, so as we're going through the database here, your database server is going to look at the first row, and it's going to say, is this guy's ID 1? And the answer is yes. So it's going to return the ID and name for the student where ID was equal to 1. Well, then it's going to go to the next row in the table. It's going to say, okay, well, is this student's ID 1, or does 1 equal 1? Okay, so obviously 2 does not equal 1, so the first part of that clause fails, but only one or the other have to be true in order for this query to succeed. And as you can see, since 1 equals 1, that always evaluates to a Boolean value of true. Even though the ID was 2, this part always 100% of the time is going to return true for each and every record in that database table. So what we've done here is basically tricked it into thinking that the result is always true, even though it's not, and it's going to return all the records to us, even though it shouldn't. Okay, so hopefully that's clear, and we're going to see a nice in-depth hands-on example in the office hours this Wednesday if you're interested. And so let's take a look at the last example here. This one's a little bit different. It's a little bit more malicious, in fact. I'm doing the same thing here. So I'm saying return the data if the ID is 1 or 1 equals 1, which again, 100% of the time, 1 equals 1 is going to evaluate to true. So what that's going to do is it's going to return all of the data to us, incorrectly so. But then once that's done, you can see that what I've done, I didn't stop the query there. I actually added another SQL statement, and I added drop table students. So after I've had the entire result set returned to me, then I'm going into the database, and drop table means delete. That means delete the table named students. So what I've done is I've taken all your data, gotten a copy of it for myself, and then I went in and deleted your copy right behind it. So you could see how potentially, for example, I could take your data, delete it on your end, and then maybe hold the data hostage from you or for ransom or something like that, and maybe offer to sell it back to you if you don't have a proper database backup or something, for example. So you can see here that we're able to successfully inject code because the inputs were not carefully checked, and we passed the user's input directly into our query. And we're going to see some countermeasures for this and how it can be relatively easily prevented in the next slides. We talked on the previous slide how it's possible to trick a database into returning all the data to you by using that ID equals 1 or 1 equals 1 trick, since 1 equals 1 always returns true. And I showed you a malicious example of how I could potentially just delete an entire database table by tacking on an additional query in addition to the one being executed. But I just wanted to briefly show you that there are some other things that might be very useful for an attacker to cause some damage on your website, either your web server itself or maybe the database server. So one thing I can do is I can get a list of all the users from the database. And I showed the query here for doing that, just a simple select user from mysql.user. So one of the default tables that MySQL server maintains is called mysql.user. Contains a list of all users in the database. So if the database user you have, for example, that you're using to execute your query from the web does not have, say, DBA or database administrator privileges, you might be able to find out which users there are that you could use to be able to execute more significant or more severe commands as part of your injection attack. Another thing you could do if you wanted, you could find the host name and the IP of the database server. So even though you're just filling out a simple field on an HTML page, if you do the select at hostname and you're able to successfully inject this into one of the fields on the form, then you can find out the actual hostname and IP of the database server. And once you know that, you're susceptible to a number of other attacks. So that's not good to let that information be known either. And then finally, we're not sure what other databases might be installed on that server. So it's possible that it might have some student account information in one database, but there might be another database on that server that actually contains employee financial data or something like that. So sure, we can drop the students table, but we can also get a list of all databases and see what else is being stored on that server. And then once we know that, we can launch subsequent injection attacks to either delete that data, alter it, to steal it, a number of things. But this kind of only works, as we mentioned before, when you kind of poke at the server and you give it a few invalid inputs and you see how the server responds. For example, one of the most common things to do is to type into a blank form field a simple single apostrophe. And what's going to happen is the SQL server behind it is susceptible to injection. Then it's going to give you an error message that says that apostrophe is not exactly a part of a valid SQL command. In other words, it's trying to take your input and it's trying to make it part of a query, but because you gave it an invalid character, it's not able to execute that query. So what that's telling you right there is if the server barks about an invalid input that it can't execute the query, you know that the server is vulnerable to injection. So to combat this, server administrators stopped throwing those messages because they didn't want to be overtly clear to someone who just typed a slash that they were vulnerable to injection. So what they started doing was trying to obfuscate their error messages and, basically say, okay, something went wrong, say random database error thrown. It doesn't say very much to the end user because they're not able to do much with that message in terms of understanding whether or not your server is susceptible to injection. But the problem is that it never actually went and fixed the underlying injection vulnerability. So the question became to hackers, is there a way to be able to tell, in spite of these vague error messages, whether or not a server is still susceptible to injection? And it turns out that there is a way, and there's a method called blind SQL injection, which we're going to talk about on the next slide. And by the way, if you're interested, I included a link down here at the bottom. So some of these queries I gave you up top were pulled from this site, and they're very common across instances of MySQL. But there's a whole long list at the link below. So if you're interested in other things that you can do against the database server through injection attacks, I encourage you definitely take a look at that cheat sheet for some more commands. Now let's go ahead and take a look at how a blind SQL injection attack actually works. So let's say our first step here was to see if this SQL server is subject to injection attacks. As we said before, we can just type in a simple apostrophe and see what kind of error messages return back to us. But in this case, let's say we do that and we get something that's not very useful and it just says database error. Okay, I don't really know what that means. I don't know if it means it's susceptible to injection. I don't know if the database server happens to be down right now. I don't know if I issued just an invalid query. Can't really be sure. So we'll talk about how we can basically ask a series of true-false questions of the database, and we'll see how the server answers it. And based on the questions that we ask it, we'll be able to determine whether or not that database server is susceptible to an injection attack. So the very first answer here, the very first example here, you see I've made a query that might look familiar to you if you've ever seen a page with PHP with SQL in it before. So it's visiting a football.com/ a PHP page called players, and it's querying it with an ID value of 2. So if we are just building the query based on the user input here, you can clearly see that we're passing in an ID of 2. So I'm going to select name and number from players where ID equals 2, which was passed in from the form field. And that's a perfectly valid, fair query. So this is going to return the name and number for the player who has an ID of 2. So nothing special about that. That's the database working as it should on a perfectly legal and perfectly valid and safe input. So the next case, we're going to do the same thing, but we're going to add a little bit to the end of the query, as you can see. So in this case, we're still going to query the players.php page with an ID of 2, but not only do we want the ID to be equal to 2, we also want it to be the case that 1 equals 2, which you and I know will never ever happen. Therefore, this AND condition can never ever ever happen. So when we try to do that from the database, select name number from players where ID is equal to 2 and where false, right? That AND condition, again, never comes true, so the result should be nothing. The result set will be completely empty. And finally, we're going to just do the opposite of what we did in step 2. We're going to query again for player ID 2, and this time we're going to give it the clause that 1 equals 1. So again, we want both of these conditions to be true in order to return any data. So we're going to select name number from players where ID is 2 and true. So the only case where this happens, of course, the 1 equals 1 is always true, but the only place where ID is equal to 2 is for player number 2. Okay, so that does occur one place in the database. And so we would expect that this would return the record, so the name and number for the player with ID equal to 2. So my question for you is, what do these results that we saw in these 3 steps, what do they lead us to conclude about whether or not this site is susceptible to SQL injection? And I'll give you just a couple seconds to think about that. What we can conclude here is that this database server is indeed injectable. So the very first query worked as expected. So there's nothing to glean from step 1. But the difference between step 2 and step 3, since step 2 correctly answered nothing, and since step 3 correctly answered with the record for the player with ID 2, we can see that it is directly taking the inputs that we gave it and it's executing them against the database. So in spite of the vague message that we saw when we tried to type an apostrophe in the box, we're able to clearly tell here that in step 2, we were expecting to see no results, and we did. And in step 3, we were clearly expecting to see the results for the player with ID number 2, and we did. So we can take those 2 outcomes and we can blindly assure ourselves that the inputs that we're giving it are being interpreted literally and they're being passed in as part of the query string. And that's exactly what makes a database server vulnerable to injection. All the talk of injection attacks might be a little bit scary, but as we saw with cross-site scripting, which was fairly easy to prevent, SQL injection is basically equally easy to prevent. So as we said last week, the number one thing that you have to do when you're reading input in from a user, you have to do some sort of analysis of that input. And once you've analyzed it, you need to sanitize it or encode the data. And we talked about this on the message boards last week, but what you get by encoding data or escaping data is you take whatever the user types in and you make absolutely sure to treat it more or less as just straight text. Even if a user did type in a malicious query, if the SQL query just sees it as a simple string, it's not going to actually use those malicious characters and try to build a malicious query out of it. It's just going to treat it as plain old blob of text, and that's it. So in a sense, it's almost not executable. It can't be used to tack on to the query. You can't add a semicolon drop table students afterwards, because it's not actually going to execute that code. It's just going to use it in the where clause, for example, if that's where it's at or whatever. It's just going to see it as plain text, and it's not going to be executable against the database. So that's the number one thing. The number one thing far and away is to perform very close encoding, escaping, or sanitization of the inputs. So the inputs from the user can never be trusted. The other nice thing that has come into existence since SQL injection attacks were discovered is something called a parameterized or a prepared query. And these are actually pretty neat, and they're supported in a number of languages. In fact, in PHP 7, they completely deprecated the use of their previous query functions for SQL databases, and now they only allow you to use something called a parameterized query. And a parameterized query is simply this. You type the query that you're interested in executing. So for example, I may want to say select name from students where ID equals blank. And when I say blank, I mean I'm reading that value in from a form field from the user. Okay? As you know, I can't trust that. So what the language does for you is they take that query and they precompile it. So think of it as turning the query into a function, and the function has one parameter, and that parameter is going to be that ID field that the user is passing in from the form. Okay? So what happens is when you execute this query, since it's precompiled, there are no other options that can be passed in that are valid except for basically an integer, right? Because you're looking for an ID in this case. So the function knows that you're matching on an integer because it knows the type of the ID column in your database table. So it is simply binding that argument to a specific data type. And if it doesn't get anything, or if it gets something other than an integer, then the parameterized query is going to bark and not allow you to execute it. So since you're doing this nice tightly binding the types to the data that's coming in, if there's any kind of mismatch, in other words, if there's an attempt at a SQL injection, it's impossible for it to be successful. So that's obviously a really, really nice facet of these parameterized queries. The other thing that's really nice about them is they execute faster. So previously, when the functions or when the queries were not precompiled into functions, every time someone wanted to execute the query against the database, the thing called the query planner and the query optimizer took the query as input and had to build it and execute it each time. In this case, the query planning and the query optimization steps don't actually have to take place each time because they've been precompiled into functions ahead of time before use. So they're actually much faster to operate, especially if you're doing a lot of frequent calls to the same query. And just for the sake of it, I wanted you guys to see below, this is an example of a parameterized query. You might see something like this in the assignment. This is written in PHP. So you can see here, we are preparing a SQL query that's called insert into a table called registry. And we want to insert into two columns. We want to insert a value into the name column, and we want to insert a value into the value column. And what do we want to insert there? We want to insert values called a variable name, so that's colon name, and a variable value, that's colon value. Okay, so those are the two inputs that are going to be read in from the user. And then you can see here what we're doing is we're binding those two parameters. So $name would be the variable that was read in from the user input, and we're taking that and assigning it to the colon name, which is the parameter to the prepared query above. And the same thing with value. $value was read in from the user. We're binding that to the colon value, and that's also going to get passed into the prepared query. And so since we know these data types ahead of time, again, the prepared query guarantees us that the only acceptable value for name is a string, and probably the only acceptable value for value is numeric. So there's no way that a SQL injection attempt can possibly be successful if we're using prepared or parameterized SQL queries. The final thing I figured we'd talk about this week is a little bit about the infrastructure and the network setup surrounding an architecture that involves a web, a database, and possibly an application server as well. So sometimes it can be the case that the web and the application server are hosted together, and that can mostly be okay, I think, although best practice says to separate your web, application, and database server physically if possible, but if not, at least in the sense of virtual machines, 3 different virtual machines, 1 for each role. But one thing that should never happen is your database should never ever be publicly facing. So the people on the web can't query it publicly, but that's a problem in a sense, right? Because our internet server, our web server, is publicly available, and we do want that to be able to have access to the database. So the question becomes, how are we able to segment the network in such a way that people can still publicly access my internet-facing web server, but they can't publicly access my private backend database or potentially application server? You can see in the diagram below, a client on the left is connecting in through the internet. So they type our website, which is google.com, and it resolves to 1.2.3.4. So that sends us to the outside interface on that first firewall there. So after the first firewall, you see there's our web server. So it's sitting in something called a DMZ, which in a network sense means a demilitarized zone. We put things in the DMZ that we want to be publicly available, but that we're kind of okay, more or less, with them kind of the machines getting beat on a little bit. So we don't, it's okay if the web server goes down, we can stand up another one to take its place. It doesn't hold any specific critical or valuable data. And we're willing to see the fact that, okay, if someone comes in through the open internet on port 80, you can have access to this server. That's kind of fine. But what we really don't want is for people to be able to get past that second firewall directly to the database server. So what we do is we stick the web server in between the 2 firewalls, as you see there. And though they're drawn separately as 2 different physical firewalls, these could just be 2 virtual interfaces on different VLANs on the same firewall. Okay, so the public internet has access to the web server, and the web server has access to the database server. But notice that a client connecting from the internet, doesn't have direct access to the database server. So the web server is basically a proxy. You can't get data from the database without going through the web server. So in theory, if the interface that you put forth on the web server is a good one, and it's carefully written and not carelessly written, then you can more or less fully control who has access to which data on which database. You can control when, you control what queries they can run, things like that. So I wanted you to see how granted this is a very small rendition of a web database server architecture, but I did want you to get a little bit of a feel for the network side on how these things can be set up. So we'll talk a little bit more about different VLAN concepts and some of the routing, the firewall rules, and virtual interfaces that come into play here during the office hour this week. So if you're interested in hearing some more about this, please feel free to join us on Wednesday night. I hope you enjoyed the lecture. Again, this was a sort of a deeper dive on some of the server side of things. Specifically, I wanted to focus a little bit on databases this week. We're going to talk a little bit about application layer security about 2 or 3 weeks from now. So a little bit deeper discussion there is still to come. So I hope you enjoyed it. We're going to look at some SQL injection attacks. You're going to try to launch your own in this week's assignment. So I hope you find that fun and exciting. If you have any questions, as always, please feel free just to email me and let me know.